So, hello everyone. I am Ismail. I work at data at SVT, which is Swedish television. What's your name?
I'm Dan.
Nice to meet you. Yeah, it would be very unpractical to ask for everybody's name. So, this presentation does involve cats. So, if you are allergic to that, please, there's a door over there. Now, the reason I want to talk about cats, though, is to talk about a problem that is very common in machine learning. So let's imagine this. Now, you are working at a cat hospital. There is such a thing in a place called the Cat Citadel, or the Citadel of the Cats. That is your choice. So in that hospital, you receive 132 cats. Those were victims of jumping from the windows. Now, if you've ever had a cat, you know that cats do jump over windows. And this is the data set that you got at the hospital. But there's something weird in that data set. And the weird part is this. It seems like the higher the building is, the higher the probability of the cat surviving. Now, to tell you even more, what you notice is that in a 7-stories building, it seemed like 21 out of 22 cats, which is about 99% of the cats, actually survived the fall from the 7-story building. Now, this is usually in machine learning and data science where the domain knowledge experts come in and they tell you, well, it is because the cats are good at landing, or when the building is higher, the cats actually have a better chance of, trying to go back on their feet. But there's something fishy here. Do you get it? It's a pun. Anyway, so there's something fishy, and the fishy thing here is actually the data set itself. So when you receive the data set, you receive the data set of the cats that actually were admitted into the hospital. Now, if a cat does not survive, it usually doesn't go to a hospital. If a cat falls from a 30-floor building, it doesn't go to the hospital. On the other hand, the cats that are fine, the cats that fall from the first floor, they usually just keep being cats, right? So you don't receive them. So this is a very well-known problem in statistics, and statisticians would call this a convenience sample. So, any statisticians, by the way, in here? Yeah, there's one hand over there. That's great. So, this is a convenience sample, and what that basically means is that it is a sample that you found that was collected by someone else, and in this case, the sample is very biased. Now, you might think that this is a very far-away problem and that it's very obvious in this case, but this was actually a real problem in 1989 in an article that was published by the New York Times magazines back then. And the name of the article is "On Landing Like a Cat, It Is a Fact." Now, they made this mistake, and the reason they made this mistake is, well, on one hand, data science was not as popular back then, but it's also the fact that it is sometimes hard if you're not a statistician or if you haven't really dug deep into data science to notice these very small problems, or as some would call anti-patterns, where you follow a certain pattern that leads you to wrong results. Now, in this part, I'm supposed to tell you why you should listen to whatever I have to say, and the truth is you shouldn't, so I have to tell you that before. So please be very skeptical. Whatever I tell you might be wrong, and I will tell you most probably things that are not necessarily related directly to your domain. So please try to think of how you can apply them in your own use case. Now, to explain what an anti-pattern is when you follow a certain design pattern, and that being a certain let's say a transition of steps that you usually follow to build a system. And and it's so automatic that you keep doing that, and at some point you start ignoring the little details, and you end up in failing systems. And to give you the too long didn't watch version of whatever I'm going to say today is you have to take into account the bias in your data and try to use data models. And the second point is try to start simple and use error analysis to iterate over your models and improve them over time. Now, this will make more sense in a second. So if you want to dig deeper in the resources that I will mention or anything, any reference in this talk, please visit the link over here. Now, let's start by talking why more data is not always better or more features are not always better. And the reason this is true is because of bias. What bias is basically the difference between what you expect a certain value to be and the actual value of your estimate. Now, in this case, it is the bias over the data that you've collected. So, what happens when you collect more data? Any ideas? What happens when you collect more data is basically you get more accuracy, but the bias does not change. And this means that you get very precise wrong results. So you're very sure about your result, it's very accurate, you have very low error, but in the same time, the bias is still there. Now, to recover from this, what you can do is use a data model. So imagine that the data that you have is actually a set of observations because you do not know what's actually behind that data. So for example, if I give you all a survey to fill in, and I get the results of you filling the surveys, there are some people that will not fill the surveys. And so in between the people that I'm trying to represent, which are everyone here, and the results that I got, there are some people that did not submit results. And there's probably something in the mind of the people that did submit the results that makes them a more biased data set. And that cannot be resolved by bringing in more data or gathering or sending in more surveys. The way it can be resolved is by saying, well, how do we model the process between you getting the survey and you actually giving me the survey back? And that's, in this case, that's the observation model. And there's also a process model because at the moment I gave you the survey and at the moment I'm going to analyze the survey, you, which is what I would consider the representative sample, will change, your ideas will change, and so that would be a process model. And this is very common, for example, in trying to predict election results and such things. Now, this can be all very abstract, so let's start with a very more simple example, and let's talk about penguins. Does anyone here not like penguins? Good, everyone likes penguins, everyone loves penguins, I can imagine. Now, let's imagine that you have been admitted at the Penguin Research Society. It's a very prestigious research society. And the subject of your research is estimating penguin population size from satellite images using deep neural networks and inverse reinforcement learning. Such a cool title, right? Now let's make it simpler. Let's just say that it's estimating penguin population size from satellite images. Now this here is a satellite image of penguins, as some of you might have guessed. So your task here is to actually estimate the number of penguins in an image. But before you do that, you get a certain number of images, and before trying to build a classifier, you will need to associate an image with whether it has a penguin or it does not have a penguin. So let's make this problem simpler. Let's just say you're going to try to make sure whether an image, to make sure that you can say whether an image has penguins or does not have penguins. And you might think that that is simple, but not necessarily, because penguins are smart. Or as my friend Talia says, never underestimate a penguin. That is actually a quote. So penguins can hide under snow, penguins can hide underwater, and at the moment you are taking the picture from the satellite, you do not know whether the penguin is actually hiding or whether the penguin is underwater. So the image that you have is the observation. The number of penguins in that image is what you are trying to guess. So in this case, what you would want to do is this. You want to say, okay, in the case of us saying that there are no penguins, there's many possibilities. There's the fact that it is true and there are no penguins, and there could be the fact that it is false and there actually is a penguin. When it is false, it could be that the penguin is underwater, that the penguin is under snow, or that the penguin is there, but we cannot perceive it for some reason because satellite images are not very precise and they're not optimized for penguin research. So this is where you need domain knowledge experts to try to come up with a probability of, for example, the probability of not seeing a penguin knowing that the penguin is swimming, or the probability of the penguin swimming when you predicted that there is no penguin. So if you try to follow a representative sample of the penguin population, then you can conclude on a certain probability like this and actually come up with the observation model. Now, of course, then you would need to, then at least you have a certain representation of your bias and you have a certain control over how biased your data is. Because in the end, yes, there are going to be parameters that you cannot control, but just make sure that you are not forgetting about bias when you are collecting your data. So what about when we try to choose a model? Now, we do hear the advice of trying to keep the model as simple as possible, but that means different things for different people. So I think it is an easier matter to ask the question, if it were easy, what would it look like? Meaning, if this problem I'm trying to solve was easy, what would it actually look like? And then try to solve it yourself. As a human, how would I solve this problem myself? And once you come up with that, then you can try to choose a very simple model. Because trying to come up with the most complex neural network that uses inverse reinforcement learning, it can be cool, it can be fun, and it can sound really impressive. But in the end, it's a good sign of premature optimization where you still do not know how your data is going to react to that model, or whether that model is actually going to help you come up with better solutions. So just start very simple, gather the data, make sure that you have control over everything, have a scientific approach where you note the assumptions that you are making. And because at least that way you know I made this assumption about penguins and I can verify that later on, or I can remove that assumption when it seems like that assumption is wrong. Now, after you have this very simple model, how do you test it and how do you implement it? How do you implement it and how do you test it later on? The reason you would want to do error analysis is because you want to decide whether what you really need is more data or more features. And what an error analysis would actually look like in real life is you have a data set and you have a very simple model and you want to, let's say in this case, you are trying to predict tumors. And you have a data set that has pictures of tumors, and it tells you whether it is a benign tumor or a non-benign tumor. So what you can do is you can try to see how you can improve the accuracy of the model. And the accuracy can be, for example, the mean square error, to make it simple. So if you are trying to improve the accuracy of a certain model, you're going to see that maybe your very simple model is not enough. So maybe you need to improve on that. Or maybe what you really need is you need to make a more complex feature. And because your model is simple, then you can actually manually define what a more complex feature means. And you can actually see whether you can actually understand what that feature means. Because if you start, for example, by using deep learning, you might end up with a set of features that are combining different things from your data, but you are really not going to understand what the feature that the model concluded really means in real life. So what usually ends up, if you start by premature optimization, is you would usually end up with a very complex model that might work, but it is going to cause a lot of technical debt within the company. Because later on, you're going to recruit more people, you want them to understand how it works, and it is going to be much harder. You might want to change, for example, the data that is in production, and you might want to change the data that is in test. And if you do not have control over, if you do not have a certain way of centralizing this data, then of course you're going to end up with creating more technical debt in the future. So there's also a case where you might have very skewed data. And this would be, for example, the case of trying to detect tumors in cancer. So usually you would find that in this case, if you have a data set comprising of images of tumors and classifying those, whether it is a benign tumor or an actual tumor, what you want to do in this case is if a patient comes in and you have a picture of their tumor, you do not want to tell them that they are fine if they have a risk of developing cancer very soon. And that would be a false negative, in the sense that you are telling them that the prediction is false, but they actually have a cancer. And to avoid these problems, calculating accuracy and doing error analysis will not be enough. Because if we go back here, when you calculate error analysis, what you do is you're basically just seeing how accurate your model is. But now you want to see whether you are having more true positives or more true negatives, or whether you're having more precision and or more recall. And sometimes there's a trade-off between these two notions. And if you are not familiar with precision and recall, there's more resources on the link that I've sent you, or that I've actually shown at the beginning, and I'm going to show it later on as well. So think of precision and recall as this in the case of trying to predict tumor cells. So precision would be the fact that you are calculating the number of true positives, meaning the number of things that you have predicted to be true, that you have predicted to be true and that are actually true, over all of the things that you have predicted to be true. And recall would be the number of things that you have predicted to be true over all the things that are actually true. Now, by improving precision and recall, of course, you are improving the model, but by improving precision but usually you would find a trade-off. So if you try to improve precision more with another model, you're going to make a trade-off of recall. And in this case, you really need domain knowledge or domain expertise to conclude whether what you really need to focus on is one or the other. And there are other ways of making trade-offs, like the F-score, which is basically a formula including both precision and recall, but it does depend on the domain and it does depend on the application. And you're going to find more applications on the link that I'm going to show later as well. So, what should you take from this? It was all very general because of course, in 20 minutes, we can't really dig too deep in all of the antipatterns and all of the ways we can test our machine learning models. But what I want you to do is to try and go and take one of the examples here and try to use these simple methods or these questions of, first of all, asking yourself, if it were easy, what would it look like? And second, focus on testing. Testing both the data, your assumptions over the data, which you should, of course, gather somewhere. So whenever you make an assumption about your data, try to keep it somewhere so that you have a look at it every once in a while. And try to have a centralized place for your data. So in case the data in production changes, the data that you are testing with changes, the data that you are training with changes. Now, you're going to find that everything is more detailed in this link. And please, if you have any questions, I will be here. So thank you.